Okay, so remember our big title now is surface integrals. To define surface integrals, we start with surface parameterization. Then, in the previous lecture, we discussed the orientation of the surface as, and remember this was characterized by the normal vector, and we said that the normal vector is r sub u cross r sub v. At this stage, we are ready to define what we mean by a surface integral. Before starting surface integrals, let me remind you of the line or curve integral, just as a reminder to make some connections. So for the line integrals, we have a constant force, call it F. This force is applied to move an object from A to B. Then the work is F times the displacement, which is B minus A. Then, of course, here the F is scalar. Okay. Then, if the force is a function of x, so this time it's the same thing. You're moving an object from A to B, but this time the force value depends on the position x. So at each x there is a certain force. In this case, the work done by this force is from A to B, f of x dx, and we discussed how to move, and we discussed in class how to move from this formula to this formula by taking a partition of the interval AB. After that, we said, okay, what about if f, the force, was a vector? So if f is a constant vector, and this time, whether you're dealing with R2 or R3, you're moving an object from A to B. So this is the path from A to B. In this case, the work is F dot the displacement, and the displacement is you take the terminal minus the initial as vectors. Then we reached if F is a vector but a function. So this is a vector field. This is the meaning of a vector field. So it is a function and a vector. Then the work is the integral of dot dr. And this integral depends on the curve. We discussed this in many classes. So if you start at a point A, you end at a point B, whether you're dealing with R2 or R3, you have a curve C in this orientation, in this direction. So the integral over this curve gives you the work done by that force. We discussed this in full details. Is it path independent? If you have a closed curve, is it zero, and so on. Okay, now we want to define the surface integral. So what is the starting point? Let me call it starting point or a trigger. What is the trigger of surface integrals? So now if I ask what is the trigger for the line integral, the trigger is these details. So if you have a constant force, then you have a formula. If you have a function, then you have a formula. If you have a vector constant, you have a formula. Then the question was, what about if you have a vector field? Then we had to find a formula for the work done by that vector field. So now what is the trigger behind the surface integral? The surface integral, it's all about the flux. It is all about the flux. What do we mean exactly by the flux? So imagine you have a surface. We're dealing with R3. Imagine you have a surface. And you have a fluid, a certain fluid, and the velocity of this fluid, so the velocity is f as a vector. Remember, the velocity is a vector. So you have a fluid, a moving fluid, a current, and at each point there is a certain velocity. Imagine a river, for example. If you look at a river, at each point the velocity is different from another point. So now we want to talk about the volume of a fluid crossing this surface per unit of time. This is the definition of a flux. So in general, what is the definition of flux? So let me define it in terms of fluid. So if f, which is a function of x, y, z, represents the velocity of a certain fluid, of course at point x, y, z, and if S is a surface, the flux is defined by the volume. Let me write it just to emphasize this. It is the volume of a fluid crossing S per unit of time. This is the definition of a flux. So you have a surface. You want to see the amount, the volume of the fluid that passes or crosses this surface. Now let's recall the basic formula. So if F which is the velocity, it was a constant vector. What is the flux? Then the flux is you take F and you make a dot product with the normal vector. You take F with the dot product of the unit normal vector, this times the area of the surface S. Now, of course, to apply this, we recall this formula from physics. To apply this, we need F to be a constant vector. We need N to be constant. So what do we mean by the normal vector to be constant? That means when you draw your surface, you take any point on that surface, you find the normal vector, it has to be the same, in the same direction. And of course, it is very clear that this formula depends on N, so we're taking N as our unit normal vector. So for example, just to make this idea clear, for example, if S is the plane, for example, it could be a plane like 2x minus 3y plus 4z equals 10. In this case, what is N? We know that a normal vector for this plane is 2, negative 3, 4. But unfortunately, this is not a unit vector. So to apply our formula, we need to convert this to make this a unit normal vector. So let me write it like this, n hat. So we take 1 over the magnitude of this vector, which is the root of 2 square, negative 3 square, 4 square, that is 16, 25, 29, times 2, negative 3, and 4. So this is the vector we are using. And this is a fixed normal vector. This is a fixed unit normal vector. What do you mean by fixed? Because if you draw the plane, we know this, if you draw the plane, at any point at any point, this is your normal vector. It's the same normal vector at all points. Not only this, so now if you take f, so if f was a constant vector, then you say, okay, what is the flux? You take your f, dot product the normal vector, the unit normal vector, and times the area of the portion of the plane that you are interested in, the area of the planar, let me call it region. So for example, you're interested in this part of the plane, you compute the area of this part, and you apply your formula. This is the definition of a flux. Now, what is our concern? What is our problem? Our problem, let me say, our problem is two-folded. So we have two parts for the problem. The first thing, the second thing, the first thing, what about if f is not constant? So we're saying, okay, you can apply this formula, you can apply this formula if the force, or if we, in this case we don't call it force, it's a vector field that represents, for example, the velocity of a fluid or a current. The other problem is, what about if n is not constant? And this is very clear. The first problem is very clear. For example, if the vector field was depending on x, y, z, like this simple example. This is a vector field that depends on the point. And for example, if you take the sphere as your surface, if you take the sphere as your surface, we can see that the normal vector is not a constant. So at this point, for example, this is your normal vector, at this point this is your normal vector, and so on. So you have infinitely many different normal vectors. So this is our concern, and this is the trigger behind surface integrals. So in this part of the course for surface integrals, in fact, they are sometimes called flux integrals. For this reason, for what we are discussing now, flux integrals. So surface integrals, what they do is they compute the flux of a vector field f through any surface S. And what we're going to discuss can be applied whether f is a constant or not, whether the normal vector is a constant or not. So what we're discussing now is more general than what we did in physics for the constant vector field. So the definition, our definition, so let S be a surface with parameterization R equals R of uv, and remember when we have a parameterization, the u and v in most cases they belong to a certain domain. They're not free. For example, they could be in a rectangle, in a triangle, in a circular region, and so on. So this is my domain D, and let f be a smooth vector field. We define the surface integral of f over S by what? Let's go back just to make sense of the formula. Let's go back to the flux formula. This was the original flux formula. So you have the vector field, you have the normal vector, you have the area of the region. Now my problem is that the force is not necessarily a constant, the normal vector is not necessarily a constant, and the area, because in that case you're dealing with different pieces of the surface. So let's say this is my surface, regardless. What we'll be doing is, you take a very, very small part of this surface, for that very, very small surface, I can assume that the normal vector is constant. Also, I can assume that on that very, very small piece, and we discussed these ideas before, if you're taking a very small portion of a surface, you can assume, okay, it's not a constant, but it's almost a constant. The difference is negligible. And also you can assume that f is a constant. Again, it's not a constant, but because f is continuous, so if you have a very small portion, the difference in the f values is negligible. In that case, what is the flux of f over this very, very small piece? It will be f dot n times the area of this small, very, very small rectangle, ds, for example. Okay, so this is done over this very small piece. Imagine now you're taking all pieces over this surface. You're covering it with very small rectangles, or not rectangles, in fact, very small pieces. So first of all, for the notation, we do it as double integral. This is just the notation over s f dot n dA or ds. It depends. Some people call it ds, some people call it dA. We're talking about this s. It could be a. That's not a big deal. Okay, so this is our notation. Where did this notation come from? It comes from this notation here. Now, how do you compute this? In fact, if we do these details, if we take these small rectangles and we do exactly like what we did with the line integral when we moved from the constant vector case to the variable vector case, when we had a partition, we can do the details to end up with the double integral over d. What is d? d is the UV domain. F, yes, it is f. Let me write it on a new line. So this is the double integral over d. You take f, you substitute the parameterization dot the n, yes, what is the n? The normal vector r sub u cross r sub v d u dv. Of course, is it du or dv? This can be dv du. We know this thing. And remember, we're assuming smoothness. So as long as we're assuming smoothness, so the function is continuous, the partial derivatives exist, everything is fine. In that case, there is no difference between du dv or dv du. And this is the reason, because of the smoothness, this is why we can approximate the big curve with these small, the big surface with these small portions of the surface. If the function was not continuous, we can't do this. So this is our definition for the surface integral. So in general, so to compute a surface integral, it's very clear now that we need first of all to find a parameterization for the surface. Then it's very important to find the domain of the parameterization. It's not free. There is a domain D. Then you just do the integral. In direct computations, the difficulty is in finding the parameterization and its domain. Let's see an example. See an example. So let's take the function f as y x z, and let's take the surface as the portion of the plane x plus yz plus 1 in the first octant. Then let's find again, this is just a notation, the surface integral of f dot nda. This is the notation for the surface integral. So in my example, this is the x, y, z axis. Now this plane, what is this plane exactly? X plus y plus z equals 1. This is a plane. If you set yz equal to 0, then x is 1. If you set x and z zeros, then y is 1. The same for z is 1. So you have a plane passing through these 3 points. It's very clear it's like a slanted plane. But we're interested in this plane only in the first octant. And remember, the first octant means x, y, z are bigger than or equal to 0. So if you agree, you will get something like this. The portion of the plane will be something like this, which is just a triangle. So to do this parameterization, we need the first step, we need to find, to do this surface integral, we need to find the parameterization. So I want to parameterize my surface. What is my surface? It's a very simple surface, x plus y plus z equals 1. So if you set x to be u, y to be v, then clearly z must be 1 minus u minus v. But then the u and v are not free values. They are restricted to certain domains. For example, you can't have u as 2, because if u was 2, that means x is 2. U is exactly x. And if x was 2, you can't add y and z positive values to get 1. So in this example, what is the domain? What is the domain of uv? So if we draw the u v axis, now if you agree, the u represents the x, the v represents the y. So that means you go back to your surface. This is the surface. All these points on the plane, this is your surface. You are interested to discuss the domain of the uv. You are interested only in the xy values. That means you take all these points and project them down to the xy plane. So if you draw this again, and you look at it, you take all points, you project them down. When you project them down, you will get exactly this triangle. If you draw this in our UV plane, this is what you're gonna get. So this is one, this is one, this is your UV domain. Okay, so now how do we do the calculation? This is the definition. This is the definition. So the first step, you compute f of the parameterization. What do you mean by f of the parameterization? That means f of, what is your parameterization? It's u, v, 1 minus u minus v. So you go back to f, you replace every x by u, every y by v, and every z by 1 minus u minus v. This is my f, so the y, the first coordinate, this is it. So the first coordinate is y, but what is y? It's v. The second coordinate of f is x, which is u. The third coordinate is z, which is 1 minus u minus v. So this is f of r u v. Then you need to find the normal vector. What's the normal vector? It's r sub u cross r sub v, which is, this is I, j, k. What is r sub u? It's 1, 0, negative 1. What's r sub v? It's 0, 1, negative 1. You do this cross product. It is 1, 1, 1. And before we continue, let's look at this normal vector. It's exactly the normal vector, what we know from calculus 3. We know that if you have a plane equation, then the normal vector can be taken as the coefficient of x, coefficient of y, coefficient of z, which is 1, 1, 1. But we must find the normal vector out of our parameterization. If we have a different parameterization, we would have a different normal vector that's parallel to the original normal vector, but then that's what we're using in our integral. So now we have the normal vector, we have f, so we are ready to do the surface integral. So it's double integral. What? You take f after substituting the parameterization, which is v u 1 minus u minus v. This is dot the normal vector, which is 1, 1, 1 du dv. But if you write du dv, then you need to write the limits of the integral. I'm drawing it again here. This is the u dv. Remember, this is our domain of integration. This was 1, this was 1. Remember, to write the limits of a double integral, you always start with the outer integral. So the outer integral represents the v values. What are the v values? They are going from 0 to 1. Now once you finish the v values, remember, the u values are not from 0 to 1. What we do is you go back to each of these v values and you say, okay, I want to move in the u direction. When you move in the u direction, you don't get 0 to 1. You always start from 0, that's right. But you end up at this line. So you need to find u from this line. What is this line equation? It's u plus v equals 1. It's just a line between 2 points, which means u is 1 minus v. So the upper limit of u is 1 minus v. Now we do this integral, and I'm going to do it as a first example. So the dot product is v plus u plus 1 minus u minus v, nicely. Clearly the vu, that means 0, 1. So the first integral du is just 1 minus v dv, which is v minus v squared over 2 from 0 to 1, which is just half. So the surface integral, which is again a flux integral, so this value, it represents after all the flux of the function f through the surface, as this is how we compute the surface integral.